Let us have a rundown of the different properties of determinants, because one way of finding the determinant of a matrix is by turning it into uh, an echelon form and then multiplying all the elements along the main diagonal. Okay, so first, the determinant of a matrix and its transpose are equal. So you have an example, given matrix A, which is a 3 by 3, applying the basket weaving method, it will be equal to 4 times 0 times 1 or 0, 3 times 2 times negative 2 or negative 12, negative 1 times 1 times 1, negative 1, minus the product, negative 1, 0, and negative 2, which is 0, minus 3 times 1 times 1, that will be 3, and then 4 times 2 times 1, negative 8. So that will add up to negative 24. Next, we take the transpose of the matrix. So 4, 3, negative 1 becomes the elements of the first column. The second row becomes the elements of the second column. And the third row becomes the third column. So since it is also a 3 by 3 matrix, we apply the basket weaving method and we arrive at the same determinant of negative 24. So again, the determinant of a matrix and its transpose are equal. Next, if a matrix B can be obtained from matrix A by interchanging two rows of A, then the determinant of that matrix B will be the negative of the determinant of A. Actually, this is also true when you interchange two columns of A. The determinant of the resulting matrix will be the negative of the determinant of the original matrix. So, for the given matrix A, 4, 3, negative 1, 1, 0, 2, negative 2, 1, and 1, let us interchange rows 2 and 3. So, row 1 remains the same, 4, 3, negative 1. Your new row 2 will be negative 2, 1, and 1. And then the third row will be 1, 0, 2. So we know that the determinant of matrix A is negative 24. We then take the determinant of matrix B again by using the basket weaving method. It will give us 4 times 1 times 2 or 8 plus 3 times 1 times 1 or 3 times negative 1 or plus negative 1 times negative 2 times 0 or 0. Then minus the product of negative 1, 1, and 1, that will be positive 1, minus the product of 3, negative 2, and 2, so that will become positive 12, and minus the product of 4, 1, and 0, which is 0, and we see that the determinant is 24, which is the negative of the determinant of matrix A. So, whenever you interchange two rows or two columns of A, the determinant of the resulting matrix will be the negative of the determinant of the original matrix. Third, if a matrix A has a row or column that contains entirely of zeros, then the determinant of A is 0. We're given a 4 by 4 determinant and see that the third row consists entirely of zeros. So according to this theorem, the determinant of matrix A is equal to 0. Remember, when we were discussing about the definition of the determinant is equal to the summation of the product of A1J1, A2J2, A3J3 up to A sub nJn. So there must always be an element coming from each row. So whenever we take an element from the third row, it will always be 0. So since it is multiplied to other members or to other elements of the matrix from the first, from the second, and the fourth row, then the product will be 0. So all the addends or all the products will be 0, hence they will add up to still 0. So whenever there is a row that contains entirely of zeros or any column that contains entirely of zeros, the determinant is equal to 0. If matrix B can be obtained from matrix A by multiplying a row of A by a constant C, then the determinant of that matrix B is equal to C times the determinant of A. So considering the same matrix A, whose determinant is 24, if we multiply matrix A by the scalar -2, the determinant of matrix B will be -2 times the determinant of A. And you can verify that by getting the determinant of matrix B using the basket weaving method. Okay, so from matrix A to matrix B, where B is obtained from A by multiplying a row or a column by a constant C, the determinant of matrix B will be C times the determinant of A. Next, if matrix B can be obtained from matrix A by adding to a row R of A k multiple of row S of A, then the determinant of B is equal to the determinant of A. In other words, there will be no change in the determinant of the resulting matrix relative to the determinant of the original matrix. No? So remember this, whenever you add to a row of a matrix a multiple of another row of the same matrix, there will be no change in the determinant. So, considering the same matrix A, whose determinant is -24, let us obtain matrix B by adding to row 1 2 times row 3. Okay, so we multiply row 3, each element of row 3, by 2, and then adding it to row 1, what do we get? Negative 2 times -2 is -4 plus 4 is 0. 2 times 1 is 2 plus 3 is 5. 2 times 1 is 2 minus 1 is +1. Then we retain the second and the third row. The second and the third rows. We apply basket weaving method to B, and you can verify this. The determinant will also be -24. Okay? So if we add to a row a multiple of another row, there will be no change in the determinant. If A is an upper or a lower triangular matrix, or it is a diagonal matrix, if it is an upper or a lower triangular matrix or the diagonal matrix, the determinant of the matrix is simply the product of the elements along the main diagonal. So we are given here matrix A, which is 4 by 4, and it is an upper triangular matrix. So the determinant of A is simply the product of 3, -1, 2, and 5, which is -30. So that is exactly what we are going to do in the example that we will discuss, that we will take on. We will try to transform a matrix into either an upper or a lower triangular matrix, and then we'll simply get the product of the elements along the main diagonal, because that will lead us to the determinant of the matrix. Additional properties. Okay, 6.1 is just an extension of property 6. It is a diagonal matrix. Just like what we did earlier, the product of matrix A, which is a diagonal matrix, is simply the product of 3, -3, 4, and 1, the elements along the main diagonal, which is equal to -36. Additional property, the determinant of the product of two matrices AB is the product of their determinants. So we have here an example, and you can verify. You can multiply first the matrices and then get the determinant of the product, or you get the individual determinants of the matrices and then you multiply them, and you will see that they are identical. Alright, so we'll be making use of these properties. some of these properties in order to evaluate the determinant of a matrix. Last time, we applied the definition of determinants in finding the determinant of a given matrix. Now we will apply the properties. So the idea is to transform the matrix into either an upper or lower triangular matrix or a diagonal matrix. So we're given here